Hello, stats class. Here's 10.2D, which is wrapping up the comparing two means lesson. And we're going to talk about three things. The first is a review of what we talked about before about the robustness. It's a great word of T, which basically means that the calculations using T are resistant to skewedness. Or I've seen it also spelled skewness. I don't know which one is better. It just means that the calculations we're learning to do are still pretty accurate, even if the shape is not perfect. And that's that 15-30 rule that we've talked about before. I think I won't write it out again, but the 15-30 rule applies still. Maybe I'll say it out loud to reward people who are actually watching this video. 15-30 means under 15 has to be just about perfectly symmetric. Between 15 and 30, it's okay to be a little bit skewed. And over 30, we don't worry about the shape. Any shape is fine. So that was the first thing I wanted to remind you of. Second thing is talking about experiments and how that changes our significance tests or confidence intervals. So things that change when you're working with an experiment. Let's talk about that a little bit. So here's an example just to remind you of some chapter 4 stuff. We've got a bunch of volunteers, which with pain, that's an N. I can't spell. Or today I can't. They have some kind of pain going on. Maybe they have similar injuries or something. And we take all of our volunteers and we randomly assign them to two groups. And the first group gets magnets because magnets are, theoretically supposed to help with pain. And the second group gets non-magnets. They get a placebo that feels like a magnet. So they get a piece of metal that they're not told is not a magnet, and that's their placebo. And they hold it up against the part of them that hurts, and then they have to rate their pain on a scale of 1 to 10 or something like that. And we're comparing the mean ratings for these people that had magnets versus not. So there's a standard experimental design chart that we learned how to do in chapter 4. So let's talk about how we would write our hypotheses and all of that correctly. In fact, I'm going to talk about all 4 steps, but I'm only going to talk about the parts that are different. So step 1, we would have our null hypothesis, which is that the magnets have the same mean rating of pain as the non-magnets. And the alternate would be that, well, we think that the magnet would have less pain, right? We would think that the mean pain rating for the magnet group would be less. So here's how to write it correctly and incorrectly. And we've talked about this a little bit already. I'm going to write it wrong first, and you're going to hopefully realize that it's wrong, and then I'm going to fix it. So you could do it wrong by saying the mean pain rating for patients in the magnet group. And if we were in class, I would be asking someone to tell me what is wrong with that. It seems so logical that you just want to talk about these people who got the magnets, right? It's wrong because that's the sample. This is the sample or the people actually tested. You want to write about the population. So what would be better to be to say patients who would use magnets to reduce pain, which is about the population. So be careful to not write your null and alternate about the people who were actually in the study, because that's the sample. We want our hypothesis to be about everybody who could possibly use this treatment. And then the alternate or the other parameter would be the same, mean pain rating, for you could say the non-magnet group, and that would be wrong. I'll write it wrong again first. Don't say non-magnet group because that's the sample again. Instead, you'd want to say for patients who would not have magnets. So it's, you write, the word would is really important here. Who would experience pain relief without the magnets or something like that. So you always want to write about what hypothetically would happen if every possible patient got these treatments. So it's pretty common to write for patients like those in this study. Or something like that. So that's a key thing that's really hard to get right on an experiment. It's easier with a sample, but we've already talked about it with samples, so I just wanted to make sure you thought about that with experiments. Maybe I should put an experiment on this next quiz, don't you think? Step 2 mostly is the same, but not quite all the same. Random. Instead of saying yes given, you would hopefully say yes randomly assigned treatments, because it's not a random sample, it's assigned treatments. Normal would be the same exact thing as for a survey, so I'm not going to write anything more about that. Independent changes with experiments, and I mentioned this before. Independent is covered by that randomly assigned treatments thing. So you could just either leave it out, or you can just say yes because randomly assigned treatments. So in other words, you don't have to check the 10% rule or the separate samples or anything like that for experiments. I don't think they would mark you down if you did it by accident, but I actually haven't graded a problem like that in the AP test yet, so I should probably find that out. But in general, it's easier to check the independent thing for experiments because it's just based on the randomly assigned treatments. Step 3, which is the calculations, are the same as for surveys, so we don't really need to talk about those right now. Step 4, the conclusion would be, again, we have to think about this hypothetical thing. So this piece also applies to the conclusion. You might say something like, we reject the null that the pain rating, once again, we want to use that word would be equal for patients like those in the study using magnets or not. Something like that in your conclusion. So talk about people who theoretically could be treated with magnets or not with magnets, and what would happen with them, or whatever this context is. So the main difference is the wording of this and this are a little bit harder, and then these are a little easier in a way. Well, maybe not the random one, but these are a little bit different looking, the conditions when you're working with an experiment. So that's a little bit about experiments. There will be some of those in your homework. And then the third thing I want to talk about, last thing for today, is I want to remind you of the paired differences that we did back in chapter 9. because one of the hard things on the AP test is figuring out which procedure to do when, and these two are commonly confused. And the main difference is whether you have one sample with two measurements or two samples with one measurement, and I'll actually write that down. This would be one sample with two measurements, usually a before and after, or each person gets it twice or something like that. And this would be two samples with one measurement, not paired. And so what's interesting about this is we have the mean difference. So the mean of the differences is what we're looking at when we were doing paired differences. Mean of differences. So in other words, you find the differences first for each pair, then you average them. This is two different means. A mean 1 minus mean 2 is a difference of two means. Notice how that's backwards, the mean of the differences versus the difference of the means. That's an important distinction. This means that you average first your two separate groups, then find the difference. So it's a difference in order of operations, and it's kind of an important one because you would not want to find differences if they're not naturally in pairs. So if they're not naturally in pairs, you're doing this. If they're naturally in pairs, you want to find the differences first and then find the mean. And this is a one sample t-test, which is why it was in chapter 9, using the differences, which are usually in list 3. This is a two sample t-test using lists 1 and list 2 for your two groups, and you would not subtract them until after you find the average. So it's hard to tell sometimes which one is which, but if you comparing and contrasting them today is, I hope, will help you a little bit. So it basically choosing which one depends on the data and how it was gathered. For example, if you have two groups of patients that get two separate treatments, that's a two sample t-test. I should have had an S on it. If you have each patient does both treatments and you subtract them, that's paired. That's called repeated measures when they each do both. Type of matched pairs. That's when you subtract, then average. Paired data, one sample t-test. I think the calculator just calls it a t-test, actually. If the data is not already matched, you should not match it. That's a false, it gives you false data, really. For instance, there was an AP problem that I think I gave you in a warm-up or something sometime. If you don't remember it, I'll tell you about it now, where they had the middle schoolers and the amount of time they spent on homework in 6th grade versus 7th grade. And they asked, well, wouldn't it be better to just take the top person who spends the most time in this grade and the person who spends the most time in that grade and put them together as a pair? Wouldn't that be great? But the problem is that doesn't actually work. It actually gives you a false sense. It gives you a very significant test, which is not really true. So yeah, you're not supposed to do it that way. It should be matched before you analyze the data, before you gather the data even. The matched pairs have to happen first. And this matched pairs thing is technically blocks of size 2. All right, and that is enough notes for today, and we will review on Wednesday. And I think I'm going to make a recording of the chart for Wednesday, but well, yeah, you'll see that later.